All right, so continuing on class 21, we move on to turbulent flow. We already kind of introduced this, so I guess a little bit of redundancy. So we have laminar, which is below, in pipes, which is below 2100. It's slow and sticky. And then above 4000, we have fast and chaotic. Below 2100 in the laminar region. The viscous forces are much larger than the inertial forces, whereas the opposite is true for turbulent flow. The inertial forces overwhelm the viscous forces. And so one method of trying to work through this problem, and I've already kind of introduced it, so I'm kind of being, I think I'm being redundant here in my videos. I could be more efficient, is to apply Buckingham Pi and find how these are related, how the major players are related to each other. And what comes out of that, so we start out and say that the pressure is a function of a number of things: the velocity, the density, the length of the pipe, the roughness of the pipe, and the viscosity of the fluid and the density of the fluid. And we get, and out of that we get the Buckingham Pi terms of a delta P divided by 1/2 rho V squared. That's our primary pi term. The 1/2 being in there, added in there to make this similar to what we use in Bernoulli. And then the other dependent pi terms we find we have Reynolds number, which we almost always sort of run across, right? We have a length to diameter ratio, and that makes sense because it's we have two terms that are based on length. We also have another term that's based on length, which is going to be this roughness. It's where they show the I think I have another figure where it kind of shows you, it's sort of like this quasi depth, and it's not really the depth. It's sort of like just an average value that gets used. So we'll find a table that we can put the things in. So we end up getting a Moody diagram, and we create something called F, the Darcy friction factor, and we say that guy is sort of a combination of this. This is the Euler number, non-dimensional number, and we also use this guy right here. We kind of combine them together to make this Darcy friction factor, and we say that we take Reynolds number and then the roughness ratio right there, and that's what the Moody diagram, which we just showed a second ago. Let's see, bring it back. Bring back Moody. Here's your Moody diagram right there, and you can see that we have Reynolds number, we have the Darcy friction factor, and we have roughness right in there. You can kind of see that it's kind of like constant over after this thing called the wholly turbulent flow, right? So when it really gets completely turbulent right there, there's no amount of laminar suggestion at all. These are almost horizontal lines. That's an interesting thing to observe, completely based on the amount of roughness taking place. And we use, by the way, so we can use this head law, the loss in Bernoulli 2, right? So that's typically what we'll do. So we have P2 over gamma plus V2 squared over 2G plus Z2 is going to be equal to, right? So there's the resulting, and then here's the initial. This is supposed to be, 1. Okay, sorry. Almost lost my place there. And we say that's going to be, we're going to subtract out head losses. And those head losses, we're going to have major losses and minor losses. And today's class is all about the major losses. And this is really just a pipe pressure drop. Whereas the minor losses are due to fittings like elbows and stuff, valves. It could be other things like a filter might be in there, or we also have the entrances and the exits coming in and out of tanks or reservoirs and that type of thing. And this is all due to the stirring up and turbulence causing viscous losses. And straight pipe is a pretty decent. There's not a whole lot of except for the viscosity. Robbing some things away. As long it's when you start to change directions and it has to go through something where it sort of kind of stirs everything up that you end up getting some more additional losses. So the major losses and the minor losses are sort of misnomers. So just be aware that they're, even though the minor losses can be bigger than the major losses. One last thing to put in here in the introduction to the major losses and the turbulent flow is this idea of roughness. And I think that zoomed in, you can kind of see where you get these nooks and crannies where the fluid can go into there. And really this roughness is sort of an equivalent roughness. I think there is a table in Sengel where they bring this up. And I hate to always be using all these resources from Munson when Sengel is the book that we got designated, but that's just kind of how the cookie crumbles sometimes into this. Do I have other stuff to do in here? Boy, I have a lot of equipment. Okay, so I'm going to do some... so some of this is actually going to get carried over into the next class. So I'm only going to do one example, and I'm going to separate that into a separate video. But I just wanted to point out in your book where the surface roughness was. If I can find it. If I can find it. Well, that was a weird voice, wasn't it? Boom. Oh, look, they have other stuff for non-circular pipes in this one. Oh, that's good. That's nice. There you go. So here is your, in your book, here is your equivalent roughness values for commercial pipes. There's some amount of deviation in between these, so I would point that out to you. But a lot of times we're just going to use commercial steel pipe and use this value right here. We might go galvanized iron, but we go cast iron. But probably not concrete because we're not civil engineers. We're like mostly mechanical engineers in our class. So that's the end of this video where we're talking about how we're getting the treatment for turbulent pipe, and we're going to do an example in the next video. Ta-da.